Hi everyone, this is lecture 9 of my lecture series. This is about computation of moment of a 3D force about a point or about an inclined axis. So in order for you to understand the solutions here where I present, you have to gun, go, you have to watch my previous lecture videos about the principles in computing the moment of a force about a point or about an inclined axis. So here we go. Sample 9.1. By the scalar and right thumb rule, compute the magnitude of the moment of the force F about point A. So this is the figure. So first we're going to uh, resolve the 180 Newton force into its components. So it is equal to 180 times 3i, quantity 3i, minus 4j plus 5k, all over square root of 3 square plus 4 square plus 5 square. So the force F is equal to 76.37i minus 101.8j plus 127.3k. So let's draw another figure and put the components of the force so that we can analyze the moment about point A by the right thumb rule. So by the right thumb rule, moment about x, so position your right thumb towards the positive x-axis. So it is equal to 101.8 times 2.7, then minus 127.3 times 1.2. So that's the moment about ax. So moment about AX is 122.1 Newton meter. Moment about AY, position your right thumb towards the positive Y axis. So it is 76.37 times 2.7 minus 127.3 times 5.4. So MAY equals negative 481.2 Newton meter. Then moment about AZ, so position your right thumb, it is positive 76.37 times 1.2, that's the positive direction, minus 101.8 times 5.4. So MAZ equals negative 458.1 Newton meter. So in the magnitude of the moment about A is square root of 122.1 square plus 481.2 square plus 458.1 square. So MA equals 675.5 Newton meter. So that's the magnitude. We are only asked about the magnitude. So in vector form, moment about A is equal to RAF, REAF cross the force. So in vector form, so where REF is equal to 1.2 I, 2 minus, negative 5.4 I minus 1.2 J and plus 2.7 K. So we have RAF cross F, where AF is 5.4, negative 1.2, then 2.7 K. And components of the force, then IGK, and copy the first two column elements. Evaluate, it's like evaluating the determinant of a 3 by 3 matrix. So for I, negative 1.2 times 127.3 and minus negative 101.8 times 2.7, that's that is equal to 1 to 2.1 I. Then for J, 2.7 times 76.37 minus 127.3 times 5.4, so for 8, negative 481.2. Then for K, 5.4 times negative 101.8 minus 76.37 times negative 1.2. So you can check that. So therefore, the magnitude is the same, 675.5 Newton meter. So let's proceed to the second example. By the scalar and right thumb rule, compute the magnitude of the moment of the force F about point A. So this is the given figure. So this time the components of the force are already given. So this is the x. So 60 should be leftward, 90 should be upward, and 40 should be forward. based on the orientation. So moment about AX is 94, sorry, 90 times 2.4, this is the positive sense. 90 times 2.4, then plus 40 times 4.5. So we have MAX equals 396.0 Newton meter. MAY, position your right thumb towards the y-axis. So we have positive 60 times, so this is the positive sense. So 60 times 2.4 minus 40 times 6, that's MAY. So minus 40 times 6, that's negative 96.0 Newton meter. Then MAZ is 60 times, so this is the positive sense. So 60 times 4.5, then plus 90 times 6. 60 times 4.5 is 90 times 6. So MAZ is 810.0 Newton meter. So the magnitude, square root of 396 square plus 96 square plus 810 square. So moment about point A is equal to 906.7 Newton meter. For the other solution, we use vector form. So moment about A is RAF. So imagine this is point F. Cross the force, where AF is 6I plus 4.5J, then minus, it's backward 2.4K. So in vector form, it is RAF cross the force, where AF is 6, 4.5, negative 2.4. So first row. Then components of force, negative 60, 90, 40, IJK. Then copy the first two column elements. So evaluate 4.5 times 40 minus 90 times negative 2.4. You will get 396I. Then for J, negative 2.4 times negative 60 minus 40 times 6, you will get negative 96J. Then for K, 60 times 90 minus negative 60 times, you will get 810K. So the magnitude is the same. Example 9.3, a cable attached to the structure shown is staked to the ground with developed tension of 1.6 kilonewtons. Determine the magnitude of the moment of this force about the base A, solved in two methods. So first, by right thumb rule, let's uh, resolve the force into its components. So we have 1.6 times the direction is 1.5i, quantity 1.5i, then minus 2.4j, then minus 0.75k, divided by the magnitude of that distance. So 1.5i minus 2.4j minus 0.75k divided by square root of 1.5 square plus 2.4 square plus 0.75 square. So the magnitude or the force in vector form is 0.8197I minus 1.312J minus 0.4099K. So let's transmit these components at point C. You can also transmit it at point P with whichever point you want to apply them. So we have these components here, 0.8197 positive towards X, then 1.312 downward and backward 0.4099. So moment about AX is 1.31. This is the positive sense, so 1.312 times 1.8 minus 0.4099 times 2.4 times 2.4. So MAX is equal to 1.378 kilonewton meter. MAY, position your right thumb towards the positive y-axis through A, we have 0.8197 times 1.8. That's only the solution because 0.4099 passes through the y-axis. So MAY is only 0.8197 times 1.8. So 1.475 kilonewton meter. Then MAZ here, so we have negative point, this is the positive sense, negative 0.8197 times 2.4 Then because this component passes through AZ, so that's the only moment, negative 0.8197 times 2.4. And it is equal to negative 1.967 kilonewton meter. Therefore, the magnitude of the moment is square root of 1.378 square plus 1.475 square plus 1.967 square. The magnitude of moment about A is 2.818 kilonewton meter. Then for the vector approach, it is RAC cross the force, or it may also be RAB cross the force. So let's apply this. So we have AC is along X 0, then along Y 2.4, along Z 1.8. So these are the components of our AC. The components of force, then unit vectors, copy the first two column elements. So for I, we have 2.4 times negative 0.4099 minus negative 1.312 times 1.8. You will get 1.378 I, just like this component here. Then for J, we have 1.8 times 0.8197 minus 0. For K, so you'll get 1.475. For K, 0 and minus 0.8197 times 2.4, just like this. So you'll get negative 1.967K. So the magnitude is the same. So you can also try by the vector approach, RAD cross the force. RAD cross the force. So let's do that. AD is 1.5I, 0, 0J, then 1.8 minus 0.75, 1.05K. So we have 1.50, 1.05, then 0.8197 components of force, then unit vectors, copy the first two columns, then compute. So for I, we have 0 minus negative 1.312 times 1.05. That would be 1.378 I. For J, 1.05 times 0.8197. Then minus negative 0.4099 times 1.5, you'll get 1.476. So it's earlier in our solution 1.475. So the small discrepancy is attributed to rounding of values to four significant figures. Then for K, 1.5 times negative 1.312 minus 0. So we have negative 1.968. Earlier it was negative 1.967. So the magnitude is 2.820 kilonewton meter. So again, the discrepancy is due to rounding of values. Example 9.4. The 270 Newton force is applied at point A of the bracket. Determine the moments of this force about point B and about point C. So we have here the force. These are the points. So let's resolve the force into its components. So for Fx, so we have to compute this xz component first. It is 270 cosine 50. Then it is rightward. So Fx is 270 cosine 50 times cosine of 20. 270 cosine 50 times cosine of 20. So that would be equal to 160.1 newtons. Fy is this component, 270 sine of 50 degrees. That's Fy. So it is equal to 206.8 newtons. Then Fz is 270. So it is pointing backward, opposite to the positive z-axis, so negative. 270 cosine 50, then opposite sa 20, of 20, so sine times sine of 20. So negative 270 cosine 50 times sine of 20. That's Fz. It is equal to negative 59.36 newtons. Then let's draw another figure and transmit these components. So Fx 160.1, Fy 206.8, and Fz backward 59.36. So let's also solve distances. So this is 0.75, sine of 30 is 0.375, this distance here. And this vertical distance is 0.75 cosine 30, so it is equal to 0.6495 meters. So by right thumb rule, so moment about bx, remember that b and a are on the same xy plane. So moment about ax, position your right thumb towards the positive bx axis, so it is 59. This is the positive sense of 59.36 times this total distance, zero point 0.7 plus 0.6495. So 206.8 has no moment because it passes through bx axis. That's the only moment. 80.11 Newton meter. So for MBY, position right thumb towards the positive y axis. This is the positive sense. So 59.36 times 0.375 minus zero point 0.3 is 0.075. That's positive. Then this member here passes through, if you extend, passes through dy because A and B lie on the same xy plane. So that's the only moment. Positive 59.36 times 0.075 per dy. So it is equal to 4.452 Newton meter. Then finally, moment about Bz. This is the positive sense. So it is positive 163.1 times 1.3495, this total sum. Then plus 206.8 times 0.075. So 163.1 times 1.3495 plus 206.8 times 0.075. So MBZ is 235.6 Newton meter. So therefore, because we are asked to compute for the moment, so we express that in vector form. There's no mention in this question if we have to compute the magnitude. So we express that in vector form. So the answer for MB is 80.11I plus 4.452J plus 235.6K Newton meter. Then for vector form, it is R B A cross F, where B to A is 0.075I. Then you go down minus 1.3495 J. So there's no movement along the z-axis. So that's RBA, 0.075 negative 1.3495, then no movement about z-axis. Then components of force, unit vectors, copy the first two column elements. So let's evaluate the I component. Negative 1.3495 times negative 59.36 I, then minus 0, so that's the only value. It should be 80.11. Then for J, we have 0 minus negative 59.36 times 0.075, it is 4.452. Then for K, 0.075 times 206.8 minus 163.1 times negative 1.3495, so it becomes plus, so 235.6K. So 80.11I plus 4.452J plus 235.6K. Then about point C by right thumb rule, so MCX, this is the CX axis, so it is 59.36 times 1.3495 plus 206.8 times 0.6. So MCX is 204.2 Newton meter. MCY, position right thumb here, so 59 point, this is the positive sense of moment, 59.36 times 0.375, then minus 163.1 times 0.6. Minus 160.1 times 0.6. So it is negative 75.6. Then MCZ, this is the positive sense. So 163.1 times 1.3495, then plus 206.8 times 0.375. So it is equal to 297.7 Newton meter. Then for vector approach, so we have moment about C is RCA, and CA is moving to the right 0.375 I, going down negative 1.3795. So right, down, then backward. So negative zero point 0.6. Then components of force, unit vectors, then copy the first two columns, then evaluate this for I diagonal. So that should give us 204.2 I. Then for J, we have negative zero point 0.6 times 163.1 minus negative 59.36 times 0.375, you will get negative 75.6 J. For K, 0.375 times 106.8 minus 163.1 times negative 1.3495, you will get 297.7 K. So that's it. Then for example 9.5, the 240 Newton force is applied at point A. Determine the moment of this force about axis CE. So let's determine the moment this time about an inclined axis. Also express the moment of this force about axis CE in vector form. So this is the force, and this is points. This is axis CE. So I select first by computing the moment about C and the components of force 240 transferred at B by principle of transmissibility because it's easier. So the force is 240 times quantity. Let's transform it into its components. So 240 times quantity 9I, then minus 5J, then plus 4K over square root of 9 square plus 5 square plus 4 square. So in vector form, 195.6, the x component, this is the y component, this is the z component. So rightward, downward, and forward, those are the components. So by right thumb rule, moment about Cx is negative, positive moment is in that direction. So, sorry, in this direction, Cx, so negative 86.91 times 5. That's the only moment because the y component passes through Cx axis. MCy, position right thumb, is 0 because this is Cy and all the components act on the Cy axis. So MCy is 0. MCz, position right thumb towards the z axis. Positive direction is in that sense. So 185.6 times 5, and that's the only moment because the 108.6 passes through CZ axis. So 185.6 times 5. Then the lambda of CE. So lambda, unit vector of CE. So C2E, you have to move to the right 3, downward 5, so negative 5J, then backward 4, so negative 4K over square root of 3 square plus 5 square plus 4 square. So the unit vector of C is 0.4240I minus 0.7071J minus 0.5657K. So the moment about axis CE is simply the dot product of MC and lambda of CE, and that product is sum of product of corresponding components. So it is a scalar. So MCE therefore is equal to negative 434.6 times 0.4243 plus 0 times 0.7071, so 0 plus 978 times negative 0.5657. So moment about axis CE, so it is expected negative, so negative 737.7 Newton meter. It is negative because if you position the right thumb towards CE axis, the positive sense is in that sense. The direction of force is in this direction, so it's opposite, so that's why it's negative. So in vector form, we simply multiply this magnitude with the unit vector of CE. So negative 737.7 times 0.4243 I minus 0.7071 J minus 0.5657 K. So MCE is negative 313.0 I plus 521.6 J plus 417.3 K. So that's the answer. Then in another way is you try RCD cross the force, then lambda of CE. So let's write this in matrix form. So CB is 0x, 0 along x. So it's just going down. So it is negative 5j. So 0, negative 5, 0. Then components of force, unit unit vector or components of unit vector of axis CE. Copy the first two columns. Then we have 0, negative 5 times 86.91 times 0.4243, another 0, minus another 0, 0, then minus negative 0.5657 times 195.6 times negative 5. It should give us negative 737.7. So the answer is negative 737.6 because of rounding of values, as I said. Then how about the solution RCA cross F? So CA cross the force is another solution. You can also try R EB cross the force or R EA cross the force lambda of that of lambda of C. So I will demonstrate this. So CA is negative 9I, then negative 4K. So there's no Y. Then copy the first two column elements and expand in the same manner. Negative 9 times negative 108.6 times negative 0.5657 and 0 plus negative 4 times 195.6 times negative 0.7071 minus 0.4243 negative 108.6 negative 4 minus negative 0.7071 times 86.91 times negative 9, then minus 0. So you will get almost the same result, negative 731.1 Newton meter. The small discrepancy is due to this rounding off of values. And you can also try the other ways. And I hope that you will also try this in your at home in order to master these applications. Let's proceed to the last problem. Example 9.6. Determine the magnitude of the force F given that its moment about the axis BC is 300 Newton meter. So if you position your right thumb towards the BC axis, the positive sense of moment is in this direction, which is the same moment as F. So that's why its moment about axis BC, moment of the force about axis BC is expected positive. So before that, we first resolve F into its components in terms of the magnitude of F. So it is negative 2 because 5 minus 3 is 2, so 2 backward along x. So F times quantity negative 2i, 2j, positive 2j, then going down minus 3k. Divided by square root of 2 square plus 2 square plus 3 square. So in decimal, F is negative 0.4851F plus 0.4851F minus 0.7276F. Then let's transmit these components at a lambda OBC on the other hand is 0i, then positive 3j going down, 3 minus 1 is negative 2k. And divided by square root of 0 square plus 3 square plus 2 square. So lambda OBC is 0i plus 0.8321j minus 0.5547k. Then let's compute moment about V. So let's transmit the components. So MBX is 0 because all these components act on the BX axis. MBY is positive 0.7276 F times 5, and because this passes to BY, uh, yes, this passes to BY, so that's the only moment, positive 0.7276 F times 5. Then MBZ is positive 0.4851, that's the positive sense, 0.4851 times 5. And because this component passes through BZ axis, so that's the only moment, 0.4851 F times 5. So 2.4255 F Newton meter. Then in there's no need to put this in vector form. Moment about B is simply moment about axis BC is simply moment about B in vector form, then that the unit vector of BC. Since that product is scalar and the product is sum of product of corresponding components, so 0 times 0, moment about BC is 0 times 0 plus 3.638 F times 0.8321, then plus 2.4255 F times negative 0.5547. And that's it. So simplifying 300 divided by this value, we can solve F equals 178.4 newtons. Now, the direct way, scalar triple product way, so BA is just 5 and 0, 0. Then components of force. Then here the unit vectors of the axis vector. Then copy the first two column elements. Then expand 300 is equal to 5 times 0.4851 F times negative 0.5547. Then 0. Then 0. Minus 0. Then minus 0.8321 times negative 0.7276 F times 5. Then minus 0. So combining that value, that's 1.6818 F. Solving for F, it is also 178.4 newtons. Then also try in your vacant time that MBC is R D B cross F, R uh, RBD cross F, then dot lambda of BC, R CA cross F, then lambda of BC, then R CD cross F lambda of BC. So that's it. I hope that you can use this video lecture materials that I have, and I hope that it can help in your studies or it can improve yourselves. So see you in my next lecture slides. Thank you, and don't forget to subscribe.